session will be from Lund University with polar research highlights from Lund University. The first presenter is Professor Lena Ström from Lund University, and your presentation will be on Arctic vegetation is changing. Why should we care? Please, Lena, floor is yours.
Thank you. Yeah, I see that there, yes. Arctic vegetation is changing, and I decided to slim down my focus a little bit because I don't think I can talk about all Arctic vegetation change, obviously. So I'm going to do a methane perspective. And the slide you see here is changing vegetation in Abisko. And that is permafrost thaw. But I will return to that. So there comes that. This is the traditional view that I assume, take for granted that you all know, with thawing methane in Siberian thaw lakes and these bubbles forming, and the methane concentrations in the atmosphere increasing. But what we study, or I study, is rather how this vegetation affects methane emissions. What we see here, this is from Sakkenberg in northeast Greenland, funded partly by Interact, this study. And it's got this very beautiful vegetation of polar cotton grass. But this here, what you see, is not this dramatic thawing permafrost. It's rather how it looks when it's stable. So how does these plants affect methane emission in these conditions? So here we have 4 vegetation types. The F, you can read what F, fen. Very high methane emissions, up to 6 milligrams of methane per square meter and hour from this plant. And then FH, that's the hummocky fen, a little bit drier, lifted above the water table, and you see that the methane emission decrease. We then have these very dry systems with underlain by deep peat risen from the water table, and you can also see that the methane emissions are very low. So I left, if you pay attention here, I left one part blank, and that is because we also measured where these guys are not grazing. So this is, we've excluded muskoxen grazing from some parts of this fen, so you should compare, this should be compared to the fen area. The exclosures here have been there for more than 10 years now. So this is what it looked like before the pandemic in 2019. And you can then see where these plots end up. So a little bit lower methane emissions from where we have no grazing. The picture is emerging that this is because there is a dense moss layer forming. There's no muskoxen there. When they are there, they tramp on the moss, they compact it, and when they're not, we have this buildup of moss with sedges. So potentially we are making these hummocks. Even further in the future, maybe we get shrubifications when shrubs move in. But the future will tell. But it's interesting to see their big effect. You should not I mean, sometimes when you look at this, yeah, just remove the musk oxen from Greenland and you will have lower methane emissions. I don't think that would be smart, because we don't know the long-term effect, right? And we don't know what will happen if we change moss to sedge and so on. But this is what we see in what I would say is the short run. So to make it a bit more complicated, this is in Abisko. How many have been in Abisko? Yeah, quite a lot of you. And then you have seen these melting permafrost on several wetlands, I assume. Have you? Yeah. And if we just follow up with the vegetation I've been talking about, you see this high pulses underlined with permafrost. To the right, I've written dry underlined with permafrost, heath. So that's the same as Zuckerberg, which was this heath and grassland, and we see no methane emissions. When we move into these wetter areas where permafrost is thawing, we see the sedges appearing. And the sedges in the fen, as in the previous results, that's where we see a lot of methane emission. So it's not only that it gets wetter, but it also increases the methane emissions from these thawing pools. And this is, okay, so next one. And if I just divide it into what's dry and what is wet, this is an extremely dramatic effect, right? So once it becomes wet and we get these sedges, just as the Zuckerberg results show, we get this dramatic effect. Then we also did some measurements on 3 wetlands in different stages of thaw, and together with Margareta. And what we see from one of them, Kattejoki, there, it's completely thawed, or at least the active layer is very low down, or it's very deep. And then in the middle there, Kursflaket, we have a middle stage, and Storflaket, it is relatively stable and dry. Yeah, and this is what we see. So Kattejoki, thawed, more sedges, higher methane emissions, and then the 2 other sites, lower. But, okay, so now we think this is crystal clear, okay? And dry, no methane emissions, and wet and sedges, a lot of methane emissions. But this is what it looked like in spring. So we have the start of the growing season from these dry plots, which we would just assume there's no methane. We have really, really high emissions. And the wet ones are, yeah, looking as expected. But I did not, for the life of me, expect this, that the methane emission from these dry plots could be so high. Apparently, the microorganisms that make methane, produce methane, are there, even if it's not. I'm looking at the vegetation person, so I would assume, oh, there's nothing. And I told students, you can't measure there, there's nothing. That's not going to make a good project. So they went, we're going to prove you're wrong. And yes, I was wrong. So it does happen, and it would be so cool to see to what extent that happens, because it's something completely new to us. And no, I went back. Thank you.
Thank you so much, Lena, for this extremely interesting presentation.
Thank you.
I think it was so nice to see that you could see these seasonal variations. Is there any winter measurements as well?
There are automatic measurements, or rather eddy covariance and so on. ICOS is present. I don't know if it can be picked up in that, or rather, I don't know if I'm looking at Thomas, and I don't know if it would be something. I mean, you have to go to plot scale, right, to see it. Otherwise, you just get an overview signal. But do you see it?
The wind is very channeled in Arbeskesstudan, and then we have in the EC system the drier part from the one side and the wetter part, the fan side, from the other part. And then he could see big differences from the two wind directions in the methane.
But spring effects?
No spring effects, but methane emissions even during winter.
Yeah.
And rather big ones.
Yeah.
Okay, I can guess, extremely valuable data for modelers and to get the annual emissions right, to have data from 4 seasons.
I see Paul is like vaguely nodding, so we'll
Yeah.
see.
Yeah. Okay, I guess maybe you have a comment or a question, someone from the audience, or yes, please.
Mapping on methane emission over the years. Do you have any mapping on methane emissions over the years, and what's the difference between this spring and springs like 10 years ago? Or this is a new research area?
Oh, sorry.
Long-term measurements, yes.
I've had what I not like. Well, I've been there repeatedly, and before, when we measured on these pulsars, heath types, we never saw anything. So, and that's why I was telling the student that no. But so going back, I haven't seen it, and being there with students and measuring it, we haven't seen it. But then suddenly, it's there. I can say that it was a bit. There was a little bit of a whatever you call it,
Dip
in the surface. But it was also very cool that you have the presence of the microorganisms there already, because we were thinking, the vegetation have to migrate in and it will take a long time. It won't take a long time. The potential is there.
Thank you very much. Thank you.
More questions? Yes, we have one question here.
Thanks very much for the talk. I was wondering, how much do you think vegetation is driving these emissions, facilitating, or how much is it just a marker of a very highly emitting place?
I think it's a combination, because we have looked at, what comes out from the roots. A substrate for methane production is acetate. And I've looked at how much of that substrate that comes out from different species. And there is a difference. But it is, of course, very hard to distinguish between, is it because the species, that plant, exudes this, or is it because it grows in a little bit of a better condition? And so there's a lot of details to look into. And, well, it's the methanogens, the methane producers, that drive it, obviously. So then it's more about where they like to be. I would say.
Thank you.
Okay. Then, Lena, thank you very much for your presentation. And here's a hat for you, and welcome back to Abisko.
Thank you.
Perhaps you have one already. You have a lot of it.
No, I don't have it. And you should only know how much I've been talking lately about that I needed a hat.
Oh, that's good.
So,
if there will be
perfect.
one, then you can have another one later on. Thank you, Lena.
Thank you for having me.
Thanks.
Yeah, thank you.
Okay, next presenter will be Raimund Muscheler, professor at Lund University. Welcome up, Raimund. And your presentation will be on the solar signal stored in ice sheets.
Yes, thank you very much. Good morning, everybody. So I will talk a little bit how we can get the solar signal from ice cores. A little bit quick outline. First, I will tell a little bit about the sun, how the signal ends up in ice sheets, and how we do the reconstructions. So these are satellite measurements of the energy we get from the sun over the last 40 years. And only for the last 40 years we have such data. And what you see, the energy we get from the sun changes with the solar 11-year cycle. It doesn't change much. It's about 1 per mil, but obviously this influences climate. If we get more energy, it gets warmer. If we get less, it gets colder. And so we see this over the solar 11-year cycle, where the sun has more sunspots during solar maximum and no sunspots during solar minimum. And such data, sunspot data, we have for the last 400 years. And so these are telescope-based observations of the spots that people observed on the sun. And here you see that for the last 40 years, solar activity was relatively high. We see more than the 11-year cycle. We also see longer-term cycles. For example, around 1650, it was a period with almost no sunspots, and we don't really know how bright the sun was back then. And such a period of low solar activity actually seems to coincide also with colder climate. And I marked here the little ice age that kind of ended around 1850, depending on definition. But also during that time of the little ice age, solar activity was relatively low. We also had more volcanic eruptions, but we believe the sun and volcanoes contributed to this. Okay, so how does the solar signal end up in ice sheets? What we look at are actually the galactic cosmic rays. So these are high energy particles from our galaxy, accelerated in supernova explosion. And when these particles, mainly protons, come into the solar system, they see the solar magnetic field. So an active sun leads to more shielding of galactic cosmic rays. Around Earth, we have the geomagnetic shielding. Again, higher geomagnetic field, we get less galactic cosmic rays. And so we can measure that, again, over the last 50 years about. We see here in the lower panel sunspot observation again, and in the upper panel we see neutron monitor measurements which show the flux of galactic cosmic rays to Earth. So it's inverted, the blue cosmic ray flux is inverted. With high solar activity, we get less. And that we can use for going back in time, because these galactic cosmic rays, they also produce 10 beryllium in the atmosphere, so-called cosmogenic radionuclides, chlorine-36, and I guess everybody knows about radiocarbon. So again, the same thing, high solar activity, lower production of 10 beryllium and C14. So we can go back, take ice cores, measure 10 beryllium, and get a record of solar activity. So presently, we are involved in 2 big ice core projects. One is the eScript project in northeastern Greenland, that is mainly organized by the Danish colleagues in Copenhagen. And these are just some pictures from the field there. And we are also involved in the Beyond Epica project, where the goal is to get a 1.5 million year old ice core to get greenhouse gases over the mid-Pleistocene transition, where suddenly the climate changed from ice age cycles of about 40,000 years cyclicity to 100,000 years cyclicity. And so with the ice cores, we want to get the greenhouse gases, and maybe that's the key to understand this transition. These ice core projects, obviously, Polarforskningssekretariat is not mainly responsible for them, but they need to be member, need national funding, which is actually hard to get. And for Beyond Epica, we were lucky to get funding from the Crawford Foundation, 4 million Swedish crowns. So Sweden is member of this project, and any Swedish researcher who is interested can actually join, can get samples. Okay, so cosmogenic radionuclides. I said we just measure how much beryllium is in them, and then we get a solar signal. Problem is there are not many of these particles, so we need quite a bit of ice in the range of 100 to 500 grams. The sample preparation takes quite some effort, and the measurement goes with accelerators, so accelerator mass spectrometry. So it's expensive measurements that take quite some time. But this is just one result that we can get. So this is solar activity over the last 2,000 years. In the upper panel, you see a curve from 10 beryllium from Greenland. Middle panel is 10 beryllium from Antarctica. And in the lower panel, C14 from tree rings. And you see all of these curves show these major solar variations. You see the Maunder minimum, so this period without sunspots around 1650, that we see in all of these records. The agreement is quite good, but not perfect, so there are still the interpretation is not straightforward, because these particles are produced in the atmosphere, but then it depends on atmospheric circulation and snowfall rates and all of this that in the end produces our signal. But in theory, we can go back 1.5 million years with this if we get a 1.5 million year long ice core. What we also can see is solar storms, and that's relatively new. I told you now the solar effect is this indirect shielding, but with solar storms, we have first, it's basically a rapid release of magnetic energy. And with that, you can get a solar flare, which is an intense eruption of electromagnetic radiation, so X-rays. You get a particle release, so a plasma cloud of protons that leads to the geomagnetic storms on Earth, if they hit Earth. That is measured also with these interact stations, where you can measure basically the space weather. And you can get solar energetic particles events. So these are high energy protons that come basically within minutes to Earth. When we look at the last 50 years, we know when these solar storms happened, but we don't expect a big signal in cosmogenic radionuclides. So this is just theoretical calculation of the chlorine-36 production in this case, and you see again the 11-year cycle, and you see that the solar storms do a little bit of this signal, but not really much and not really visible with our data because we have quite some noise. But then the surprise came in the C14 data, where people measured year by year C14 in a tree ring, and they observed that from one year to the next, C14 levels went up a lot. And you cannot get that. You can turn the solar shielding off, you wouldn't get this signal. You can turn the geomagnetic shielding off, you wouldn't get this signal. So it had to be another process. So we went ahead, measured 10 beryllium and chlorine-36 in ice cores. And with these measurements, we saw there was also a peak in our data. By analyzing the amplitudes, we could basically confirm that this has to be a solar storm, one that is about 2 orders of magnitudes larger than anything we observed over the last 70 years. So that's kind of our main project right now. We want to measure more of this high-resolution 10 beryllium over the Holocene to start with. And we now know of 5 or so of these enormous solar storms over the last 10,000 years. There are certainly more. We just don't have the data yet. Risk assessments with these solar storms has not been done because they basically haven't been known before. And also how they link to solar activity, we don't know yet. But we basically have the solution possibly in our data where we see solar variations and then the solar storms on top of it. And so we can get with these measurements a complete reconstruction and assessment of paleo space weather. I mean, the big events, the small events over the last 50 years, we will not be able to see, I guess. Thank you, and thanks to many colleagues who contributed.
Thank you so much. Thank you, Raimund.
Thank you.
Extremely interesting, I must say. Yeah. So I'm so curious. The ice cores from Greenland and from Antarctica, you see correlation in the nuclides that you measured. And the tree rings, they were from on the globe, wherever, because it's a global process. Yeah.
Exactly.
But even though I'm interested, where did you get the tree samples from?
So C14 oxidizes to CO2 and gets well mixed.
Yes.
And these measurements come from trees from Japan, the first observations.
Yes.
But now several other chronologies have been measured and they all show the same.
Yes. It's so fascinating.
And so we have, for example, a tree ring chronology over the last about 12,000 years where everything is connected via dendrochronology. So we can go and say, we want a tree ring that grew whatever time and we can get it.
Yeah. What is your next challenge? Because now you have understood a lot, but will you elaborate a bit about the next scientific goal that you have?
Yeah, so now we see these big ones. First of all, we haven't found all, I would say, over the last 10,000 years. And there must be many more somewhere in the middle. So this one is two orders of magnitude larger than what we measured, but there must be more in between. And to get those is quite a challenge because we have noisy data. We usually need several ice cores to be sure because we have thousands of peaks, but they are just noise. So with several ice cores, we can be more sure that it's a real signal.
Thank you. Okay, questions from the audience? Yes, Magnus.
They often show up in other areas. So, I mean, the telegraph systems in the US went down in the 1870s. And so, there are historical records of events of these big solar flares. And have you been able to correlate those?
So, no. So one of the most prominent events is the Carrington event in 1859, where it's kind of the biggest known geomagnetic storm that burnt telegraph lines and so on. So we tried to find it in tree rings and in ice cores, and we can't. And the reason, I think, is these are two different things. So one is the plasma, the coronal mass ejection that comes to Earth and changes the magnetic field, but we see the high energy particles. And they can take different tracks. So the plasma comes from the center of the sun mostly. The high energy particles, they go along the magnetic field lines, so they might come from another place. So it's not easy to correlate those.
But you should, in the Arctic and the Antarctic ice, you should see those particles because that's likely where they end up, following field lines. So.
Yeah, but they need to have high energies so that they can produce the radionuclides.
Okay.
And so the plasma, we can't see. These are low, slowly moving protons. It takes 1 to 4 days to come to Earth. They can't produce our particles.
Okay.
But in this plasma cloud, you can get acceleration processes. So that theoretically, there could be a correlation, but it's not straightforward.
Thank you.
More questions?
So from the slide where you showed the solar activity in the last 2,000 years, it seems that there has been like higher activity in the last, what's that, like 100 years or so. What effect do you think that might have had in climate change, if any?
Yeah, so there was quite some debate. It calmed down a bit. So first point, the reconstruction from Greenland, I think, has a problem. We see a bigger trend than from Antarctica and from C14. And that's, I think, a problem of the Greenland data. There might be some climate influence on the deposition. For recent climate change, the sun goes down, temperature go up, so there's no discussion anymore. But in the early 20th century, from 1900 to 1950, solar activity went up quite a bit, and temperatures actually went up more than expected from greenhouse gases. So there could be a solar signal in there. But then we also have the absence of volcanic eruptions. They cooled the little ice age, and if you don't have them, you also get some warming.
Thank you.
More questions? But we also have other particles nowadays in the atmosphere that may mask the temperature rise.
Yeah, the aerosols.
Yeah.
People here who know better, but yeah.
Okay, thanks again, Raimund.
Thank you.
And this is a hat for you.
Thanks a lot.
Thank you.
Okay.
Okay, next presenter is Pontus Roldin. Welcome, Pontus. Atmospheric researcher from the Department of Physics at Lund University, and your presentation will be about aerosol particle formation in the Arctic and Antarctic.
Yes, thank you, Katrin.
Yeah. Welcome.
Thank you. Yes, so I will continue talking about particles, but not the same particles. So let's actually touch upon Raimund's presentation, since these cosmic rays, which he was talking about, they also influence the atmospheric new particle formation, especially in very clean remote regions like in polar regions. So I will mainly talk about secondary aerosol particle formation. So that is the process where aerosol particles are formed in the atmosphere by low volatile vapors which condense on nucleates and form new tiny small particles. So I will first start with an overview of different sources of aerosol particles in the Arctic. So this map is supposed to illustrate different kind of emissions. First of all, we of course have the anthropogenic emissions in the continental regions surrounding the Arctic. Here illustrated this light yellowish color here, color coded by the SO2 emissions. And that is of course transported into the Arctic also as an important source of anthropogenic influence. But then we also have a lot of different natural sources of aerosol particles or aerosol precursors in the Arctic and Antarctic. And one important source is the phytoplankton in the surface ocean, which emit a gas called dimethylsulfide, which is the main natural source of sulfur to the atmosphere globally. And this is especially pronounced emissions in the late spring, May, June in the Arctic, where you have these big algae blooms, which have I will show later, a large impact on the aerosol production. Then you actually have also impact from the animals in the Arctic, so fish, birds, mammals. They emit ammonia, and that is an important source contributing to atmospheric new particle formation in clean remote regions. So I will talk a little bit more about that also. And then of course we have the big boreal forest region surrounding the Arctic. So that is the difference between the Antarctic and the Arctic, is the huge continent surrounding the Arctic and provide this source of terpenes, which you can smell when you walk in, for instance, in a pine forest. Those compounds are oxidized and contribute to secondary aerosol formation in the boreal environment and also in the Arctic. And then finally I want to state that these huge forest fires ravaging now most of the years in Siberia, they have also large impact on the aerosol concentrations in the Arctic, for instance emitting black carbon or soot particles, and also nitrogen oxide, NOx, which influence the ozone, tropospheric ozone levels. So today I will mainly talk about natural aerosol processes and formation mechanism in the Arctic and Antarctica, and a little bit on how climate change changes these emissions, expected to change it also in the future. One obvious effect is that when the sea ice disappears, you have more open ocean, which is exposed to wind, and then you have more breaking waves, and that produces sea salt aerosol particles. So that's a feedback in the climate that when the ice is removed, you get more sea salt aerosols. But also you have more sunlight reaching the surface ocean, and that could potentially result in more algae blooms and more phytoplankton and dimethyl sulfide emissions to the atmosphere. There is also ice cores indicating that the iodine concentration in the atmosphere has been increasing quite a lot during the last 50 years, and this ice comes from Greenland. And iodine is also an important source for new aerosol particles. And then you also have the feedback with higher temperatures and increasing emissions of terpenes from the boreal forest surrounding the Arctic. And also with higher temperature, you get more drought, and especially in Siberia in the summertime, we have had these large forest fires which produce a lot of new aerosol particles, both black carbon and primary organic aerosols. But I will talk a little bit more now about this mechanism of how aerosol particles are formed from this dimethyl sulfide emitted by phytoplanktons, since this is something which we have been doing quite a lot of research on in our research group in Lund here in the last few years. And we have, together with my PhD student Robin, we have developed a detailed mechanism how to explain how this dimethyl sulfide is oxidized in the atmosphere and contribute to new aerosol particles. So this is a simplified illustration of that to represent how this DMS emission is emitted from the surface ocean, and then it is oxidized in the atmosphere by radicals, and one of those radicals are the hydroxyl radicals, which OH. And in the end, there's many reaction steps, but in the end, this DMS is ending up as strong acids, sulfuric acid, so SA here on the picture, and methylsulfonic acid, MSA. And especially sulfuric acid is known to form new aerosol particles if it clusters with ammonia molecules in the atmosphere. So this is supposed to be illustrated here in the middle figure here with the cluster formation. And once these clusters have grown large enough, they become new aerosol particles. And this is by condensation of these strong acids, both sulfuric acid and methylsulfonic acid. So here you need both the emissions from the animals, so the fish and the birds, which emit ammonia, and the dimethyl sulfide, which emits the DMS here. And once these particles then have grown by condensation to large enough size in the atmosphere, they will be prone to activate and form cloud droplets. So each cloud droplet in the atmosphere is formed by condensation of water vapor onto existing aerosol particles. And what happens with these particles, or aerosols, when they are processed through the cloud, is that a fraction of the particles with a certain size, they can activate and form these cloud droplets. But if the particles are too small, they cannot form cloud droplets. So a feature which we commonly observe in the Arctic and Antarctica is a sort of bimodal particle size distribution, where these larger particles in the bluish color here on the figures below here are supposed to illustrate that when these aerosols have been processed in a cloud, the particles which have been cloud droplets, they have grown larger because they have taken up water-soluble vapors inside the cloud. So when you get more and more cloud processing, this kind of bimodal particle size distribution structure become more apparent. So observations in the Arctic and Antarctica commonly show this kind of bimodal particle number size distribution structure. And this is of course something we want to capture also with our chemistry transport model when we model this. So we try to investigate how well we do with this. So next slide here is a study on measurements and modeling on Svalbard, and this is among others data from several stations on Svalbard, Zeppelin, which is Stockholm University, Acri station, and but also the Gruvebaden, which is more closer to the sea level. So this figure here to the left here illustrates measured and modeled particle number size distribution from Svalbard in May 2018. And we run the model both with this aerosol cloud processing and without turning off the aerosol cloud processing. And this is to illustrate that this kind of measured bimodal particle size distribution structure with two modes can only be accomplished in the model if we take into account this aerosol cloud processing. So this is not a perfect match, but there's clear evidence that this cloud processing is really essential for these aerosols in the Arctic. And we find actually similar results when we do this kind of model measurement comparison on Antarctica. So this is measurement and model particle number size distribution from a German Antarctic station Neumayer, which is not that far from Vasa, Swedish Antarctic station, also the Finnish station Aboa. And yeah, the model does a fair job in capturing this bimodal structure if we include the clouds in the model. This pie chart also illustrates the chemical composition of the modeled particles, and as can be seen from this, it is dominated by sulfate and methylsulfonic acid, and which is the sources and the DMS phytoplankton. There's also some sea spray, sodium and chlorine. Then we also investigate how the Arctic Ocean emissions of DMS influence the continent surrounding the Arctic. And my PhD student Robin has investigated here, looked at the observations from 3 Scandinavian active stations, Hyltemossa, which is not far from here, and Smer 2 station in southern Finland and Pallas in northern Finland. And he has analyzed how this particle number size distribution changes depending on how much time the area spent over the ocean, the Arctic Ocean, versus if it spent more time on over the continents. And from this clustering, you see a very clear shift in the size distribution, that you get much smaller particles when the air is coming from the ocean. You get these ultrafine particles, while when the air is coming from the continents, the particles are much larger particles in this. So that is very clear, but we don't know really why this is. So we try to model this, and we have some preliminary results from Robin here. This is modeling from this Finnish station Hyttälä in southern Finland, and this is from May to or June 2018, and that was a period when a lot of air came from the Arctic Ocean or North Atlantic Ocean during the period with phytoplankton blooms. And without the model taking into account these DMS emissions, the model substantially underestimated the particle number concentration of the continent in the boreal forest. And we do some work, so this was on natural aerosol sources, but we do also do some work and try to do source characterization of black carbon aerosol particles in the Arctic, and we set up the models and investigate that and compare with observations. Now, unfortunately, these Russian stations are not anymore, we don't have contact with them, we don't know if there is any new data, but we have some old data at least from Tiksi in Siberia coast. And here we see that the model severely underestimated black carbon concentrations, especially during the Arctic haze episode in the spring, while the model tend to capture the black carbon levels when we have these huge forest fires in Siberia in the later stages of the year. So we don't know what if we miss sources of black carbon in this Russian region of the Arctic or not. For Pallas, the Finnish station, it looks better. The model does a better job in capturing the black carbon levels. So this is a final slide. So in the future, we hope to do more work on investigating what potential effect this exploitation of the Arctic waters could result in if you have more year-round transport by shipping over Northeast Passage, for instance, between Europe and Asia, and what consequences that could have. And there's many different consequences, of course, both for the marine life and climate. But one obvious effect is black carbon emissions, which could increase, and also tropospheric ozone and the radiative forcing from those short-lived climate forces. Acidification, eutrophication, and ozone vegetation damage has been investigated with some model studies, at least, that could have a large impact. And potentially also change precipitation patterns. If you get more aerosol particles, you could potentially delay the precipitation when the air is moving inland. And what effect that has for like drought and forest fires, we don't know. And of course, air pollution health effects. So that is more on the atmospheric side. Then we of course have invasive species and noise in the underwater noise and such things, which could also inflict. But yeah, thank you very much.
Thank you, Pontus. Very interesting.
Yep.
May I spell a question, because
Yes.
I'm so
Yes.
curious on some of your thoughts about. You presented, in the beginning at your presentation at least, there was a lot of daytime reactions.
Yes,
like,
yes.
Photo-driven
Yes,
reaction.
yes,
You
yes.
mentioned the OH radical, which
yes.
is a daytime
Yes,
oxidant.
yes.
I'm a bit curious of how you think about the polar night, when it's
Yes.
because then you don't have this photo reaction.
Yes.
Have you seen reactions with nitrate radicals, or you mentioned iodine that
Yes.
can also
Yes.
survive during
Yes.
night?
Yes.
And of course you have the ice sheet, but
Yes. Yes.
so in order to model on an annual basis, what do you think about polar night?
Yes, that's a very good question. I don't have the complete answer. Most of these campaigns and the work we have done is in the summertime or springtime. But of course, aerosols and the clouds have a potentially much larger impact on as a climate contribute to climate warming in the wintertime in the Arctic. So we need definitely to understand that also. There was just a paper published this week on iodine oxidation by ozone. From the Cloud CERN consortium, and this is of course something which we want to implement in the models in the future and look into.
Yeah.
But,
you need a wintertime expedition.
Yes, we would need that.
When
definitely.
we get our new ship, we will go to the Arctic in winter.
Thank you very much.
Yeah,
Great.
so thank you.
Yeah.
But there might be questions from the audience. No, I see none. Okay. In winter, you need a
Yes,
cap.
definitely, we need that. Thank you very much.
Please, I will
Thank you.
follow your
Thank you.
research. Most
Thank you.
interesting.
Thank you.
Now we will have Dr. Paul Miller, lecturer at Lund University. And you work with ecosystem models and climate models. And the title of your presentation is Models Help Us Predict Future Changes in the Arctic. Welcome.
Thank you so much. And good morning, everyone. Let me see if I know how this works. Okay. Okay, great. I'm going to go back on land now, from the air down to land, and I'm going to talk a little bit about how models can help us look into the future. So we haven't talked about that so much so far, although Pontus touched on it at the very end there. So the first thing is to say, and this is something that you all know already, that polar ecosystems are actually undergoing rapid change. If we see, for example, that plot observations across the Arctic indicate that canopy height is increasing in pretty much all categories. The abundance of various vegetation types is increasing in pretty much in all categories. We see even just photo evidence of shrubification across the Arctic. For example, here looking at a 50-year time period between, here for example, 1949 in the year 2000, you can see the landscape or the mountain slope is becoming more and more shrubified. And then we see that in recent decades, we see satellite information is telling us that, at least in summer, that the leaf area is increasing across the Arctic, and we're getting a greening of the Arctic. Not everywhere, but over 50% of the area is experiencing a greening. And this is occurring in a place where global warming is being amplified. So global warming is being amplified in the polar regions, and we can see here that the recent temperature trends, this is from the latest IPCC report, showing us the temperature trends in the last 40 years, and we can see that the greatest increases are occurring certainly in the high latitudes, for example. You can see here that they're up to maybe 0.6 degrees per decade warming, so this is considerably larger than greater than the global average. Other key statements from the IPCC say that, for example, the special report on warming of 1.5 degrees tell us that they classified boreal and tundra, boreal forests and tundra, as particularly vulnerable to degradation and encroachment of woody shrubs with high confidence. The special report on oceans and the cryosphere projected climate-related changes to Arctic hydrology, wildfires and abrupt thaw, also with high confidence, and also a broad disappearance of Arctic near-surface permafrost in this century, and that's with consequences for the global climate, and that's with very high confidence. As well, the warming in the Arctic is likely to continue beyond the trends I just showed, at least more than double the global rate in the future. So, for example, to give you some sort of numbers, if we follow a high emission scenario in the coming 100 years, we expect a warming in the Arctic of maybe 8 to 10 degrees, which is a very, very high number. And even if we follow a scenario with low emissions, because of the amplification effect, we still expect an increase of 2.6 to 3.2 degrees by the end of the century. So that's a lot of warming, and we know that from the Arctic ecosystems are very sensitive to those temperature changes. So, if we want to look at polar ecosystems, and indeed ecosystems at the global scale, we need to be able to model these things, because vegetation and ecosystems, they're changing in response to anthropogenic climate change and CO2 increases. There's similar timescales involved. And this is expected to continue with the warming that we expect. Also, theory indicates that such changes are going to give rise to important and interacting feedback loops. They will further alter climate and atmospheric composition. We just heard from Pontus there about those aspects. And these feedbacks are also expected to change in strength and even sign, positive to negative, from place to place, season to season, year to year, etc. So I contend, at least, that one approach of trying to address these challenges are to develop process-based dynamic models of the land surface, and these crucially need to be informed by and developed with experiment, monitoring, and observations. And we need to do this to quantify and understand as well, not just quantify but understand the response of the global ecosystems in the polar regions to climate change and CO2 increases. Okay, so one such tool is known as the Dynamic Global Vegetation Model, a DGVM for short. DGVMs are models of ecosystems, and they have a bottom-up design philosophy with explicit process representations. So what does that mean? That means, for example, this example here called LPGS, which is the Lund Potsdam-Jena General Ecosystem Simulator. So we take into account, or we explicitly model processes within the ecosystem, such as primary production, photosynthesis, NPP, the growth of what we model, plant biogeography, soil biogeochemistry, etc. So we link these processes. So, for example, plants grow and die, and this carbon then ends up in the soil and it starts decomposing. So it goes into the soil model, for example, from the growth model into the soil model. We also explicitly model population and community dynamics to simulate how these plants and populations of plants compete for resources. We also include disturbances, the things that wildfires, for example, that Pontus mentioned, and other disturbances as well. And altogether, these models are very, very complex because they have lots of interlinked processes with, in some cases, uncertain parameters. And this is where the observations come in. We really need the observations to help us to improve these models. And these have been developed since the 1990s. Our model has been developed also since around the 1990s. And one thing I haven't said yet is how you run these models. So the models need inputs. So these are the forcings, as we call them, in inverted commas here. So the inputs to the models, and they include things like the climate change, the scenario you're looking at, land use and management, if you're interested in those aspects, CO2, nitrogen deposition, etc. And together, when you run your model then, they produce outputs. For example, the state of the vegetation, the ecosystems, as it changes in time. So as an example of this, for example, this is a snapshot in time of a certain simulation showing us what the vegetation looks like at a certain point in time, for example, in forested areas at various stages of the successional development and also in crops, for example. So what do we model then? These look like just abstract trees, but what do we model? We can't obviously model simulate all the species, plant species globally. So what we do is we aggregate these species into what are known as plant functional types. So, and we distinguish these plant functional types according to their various parameters or traits. For example, their bioclimatic preferences. So, for example, here, if we just compare the boreal tree with a temperate tree, a boreal needle-leaf tree like a spruce, for example, or a temperate tree like an oak, for example, then they'll have different optimal temperature for photosynthesis, different phenologies, different areas of the crown, ability to survive in shade, etc., and their longevity. So, and these and lots of other parameters as well are used to parameterize these species. And again, this is where the observations come in to help us to improve these things. And we can use, for example, these models then, going back to the greening that I just mentioned earlier on in the talk, we can use these models for examples to examine why has the greening occurred in the last recent periods. So one example of this was published a number of years ago, which they use these DGVMs, not just the one we use, but also other DGVMs, as a collection of DGVMs, to vary the inputs to the model to see if you can capture the trends that have been observed. So on the bottom, you can see, on the map top, you can see the greening trend in the map, but on the bottom, you can see a time series from 1980s to the mid-2000s, or 2010 or so. The observations go up. This indicates a greening or a leaf area increasing over time. The models can capture that trend, but the reasons why differ from place to place. In the tropics, it's mostly due to CO2 fertilization. In the high latitudes, it's mostly due to climate change. Longer growing seasons, warmer growing seasons, for example. So we can use these models really to understand the changes that are occurring. So, with polar modifications then, for polar applications, we realized a number of years ago here in Lund that we need to improve our model in order to be able to apply it to high latitudes. So some of the things that we've worked on in recent years and we're still working on are, for example, including new plant functional types which are specific to the Arctic, for example, shrub species and other Arctic plant functional types. Improving the calculation of how soil temperature changes, because that's so crucial for capturing permafrost-related issues, and also including wetlands as an ecosystem for the first time, going back to Lena's talk earlier, for example, and associated methane emissions. So when we do this, and then we can apply this model, for example, I'll just give you one example of how we can apply this model to look into the future and what we might expect as a result of climate change in the Arctic. So here, for example, is an experiment that our PhD student, Adrian Gustafsson, did, and it's soon to be published, or soon to be submitted at least. So we have an example of here, for example, on the top, in these blue colors here, tells us the vegetation biomass, the amount of carbon contained in the ecosystems. And then along the top, as well, these other tells us how the ecosystem carbon will change or increase in the coming 100 years. So this is the end of the century on a medium, like a low emission scenario to the left and a high emission scenario to the right. And then we change all the forcings. We provide the model with input, like I just said earlier, the inputs. If you provide the model inputs from various climate models and various scenarios, we can see that in pretty much all cases we get a biomass increase in the future. This line here in the time series is present day, and it goes up to the 2100 in the scenario. So we get more biomass in the future in these models. And this is because of tree line advance into the tundra areas, shrubification, for example, all the processes that we heard about earlier, these are occurring in our models. And also even in existing forests, boreal forests, they're becoming greener and denser, and also biomass is increasing there. We can also look in a bit more detail. So for example, on the top column here, we can look at by the end of the century, we expect these blue areas to have more evergreen species. The brown areas are areas where we expect more deciduous species. So, for example, temperate species starting to compete with the spruce and the pine, for example, in these areas in boreal forests. And we can also look at these on the bottom column. We can see the wood. Some areas, the green areas, are areas where we expect more woody plant functional types to exist, and the red areas are where more herbaceous vegetation will exist. And the consequences then for greenhouse gas emissions are that, for example, what we expect is so the biomass increases, but overall the carbon is, we expect more carbon uptake in the tundra regions and especially the forested regions. But now we can use other features of the model as well, and we can look at other greenhouse gas emissions. So we can look at the N2O emissions, the nitrous oxide emissions from the soil, and also the peatland methane emissions into the future as well. And we can see that in both cases they increase. So the carbon uptake from the vegetation is being counteracted by increased greenhouse gas emissions from N2O and from the wetlands that Lena mentioned. So together we can combine these using a common metric and to indicate that the net effect really depends on which scenario you're looking at. It depends on which climate model you force your model with, etc. So it's pretty much it's uncertain. But what we can say is that the uptake from carbon dioxide, or the uptake of carbon, is going to be counteracted to some degree by the increased greenhouse gas emissions from other sources. So, I've mentioned so far these are just offline studies, but of course, in reality, we know that as vegetation changes, the land surface changes, that's going to change other feedbacks to the climate system. So, one example is albedo, for example, and we expect that differs very radically between forest and open land, especially where there's snow. So as tree line is advanced, as shrubs start to become more productive, we're going to change the reflectivity of the land surface. Also, incoming short-wave radiation is going to be transferred or transformed into either latent heat due to evaporation of water or to sensible heat, heating the air. And the balance of these things is going to be changing depending on what type of vegetation we have. So together, we need to consider these feedbacks as well in addition to other feedbacks. So the standard situation you have, or we have DGVMs on the left, even if you have adaptations. You provide inputs to the model, and you get outputs of changing vegetation composition, carbon exchange, BVOCs, which influence the aerosols, and methane and nitrogen oxide, for example. And then on the other side, you have standard climate models where you provide these type of things as inputs to the model, and you get output of climate. So what we're trying to do now here in Lund is couple these things together. So we provide the outputs that our model produces, and we feed them to the climate models. Climate models then produce a new climate, taking into account the feedbacks, and update the models that way. So we get an interacting feedback loop, and these are known as Earth system models. And one example is the East Earth model we work with here in Lund University, trying to develop these things, and especially work with polar modifications to the model to improve the representation of the feedbacks that we've heard about so far. Okay, my time is running out. So just one example of this, we've projected into the future using a regional climate model to see the effect of these tree line advances. And so we can see here, for example, by the end of the century, the additional warming as a result of the tree line advance or shrubification, especially in tree line advance in this case. So we can see that in the spring, the trees that didn't exist before suddenly do exist there. They protrude above the snow, they darken the surface, and they give you warming in the spring. But in the summer, they evaporate more water, so they give you more cooling. So they change the seasonal pattern of climate change into the future if you include these feedbacks. So longer growing seasons and higher growing seasons or higher summers, warmer summers give you a warming feedback in spring and cooling in the summer. So to sum up then, process-based models, dynamic models like LPGS, like DGVMs in general, they're needed to quantify and understand the polar and global ecosystem response to climate change and CO2 increases. The offline experiments that I mentioned, they're vital for understanding the processes and the drivers, but they're very dependent on observations, monitoring, and experiment for the development and also their improvement and going forward in time. And there's a very large potential for feedbacks from other ecosystems to climate that we also need to take into account. And this makes their representation in Earth system models, like EC Earth, crucial for climate impact and mitigation studies, and especially also for policy. Thank you very much.
Thank you so much, Paul. Extremely interesting.
Thank you.
And complex. Yeah.
It's fun.
Questions from the audience? No? Yeah, yes, here. There.
Yes, so since the latest update in LPGS, quite some improvements have been made to further adapt the model to also capture the processes in the Arctic. What do you think is one of the major limitations right now for the model to fully capture the different processes and PFDs and yeah?
Yes. I would say, for example, I think it's crucial that we improve the representation of actual permafrost carbon feedbacks. I think looking forward in time, at the moment we don't really capture this if the active layer in the soil depth increases, for example, and especially these sudden events like thermokarst, etc. These really sudden sporadic events, but with disproportionately high emissions resulting from these, whether it's CO2 or methane. These are not fully captured in the model yet, and we know that they're going to be a major player in the future. So that's something we definitely need to improve. Work is ongoing, but we still haven't gotten to where we want to be.
Thanks.
Magnus?
So you need computers for this. And
yep.
So do you have enough?
That's a very good question. More, please.
Offer from the research council.
Yes, great. At the moment, for example, for Earth system modeling, which we work together very closely together with SMHI on this, and this EC Earth model was used to contribute to CMIP6, the latest climate model simulation. So we were involved in that. We were using SNCC resources on at the National Supercomputing Center, for example, and it's always a battle trying to we have to reapply for new projects all the time. It was sufficient for CMIP6, but we're going to need more power in the future, definitely.
So I've just read the new post-decision for your HPC to dedicate 10% of our European resources for climate modeling.
Okay.
So that's
good.
Millions of cores.
Excellent. That's good. Yeah,
so,
that's very good.
Look into your HPC and see what you can do. And we're channeling you through Destination Earth. But we can also apply directly, and you'll get the biggest machines in the world.
Excellent. That's good to know. Yeah, thank you so much.
Thank you, Paul.
Thank you.
And this is